Hi guys, welcome to a new video on optimization under math studies. In this video, I shall address some challenging questions in this topic, focusing on questions where they bring you a piece of cardboard with the edges cut off. So this is a specific type of questions that came in the past papers, and both questions on the screen address this topic. So I shall begin the first question shortly. The first question that we shall tackle came in paper 2, November 2001, question 8 IV. Kindly take a minute and attempt to solve, and the answer shall follow through shortly. So you are told a rectangular piece of card measures 24 centimeters by 9 centimeters. Equal squares of length x centimeters are cut from each corner of the card as shown in the diagram below. What is left is then folded to make an open box of length L centimeters and width W centimeters. Write expressions in terms of x for the length and the width. So in order to find the length, I need to calculate the remaining part of this side after the boxes have been cut off. So this is not very difficult to conceptualize. The 24 centimeters are covering three portions. This x right there, and a similar x right there, and the part that shall remain after I cut off the corners. So the part that shall remain equals 24 minus 2x. Similarly, the 9 centimeters of the width covers this x right there, a similar x right there, and the part that shall remain after I cut off the two x's, which is this part right there. So the part that I have outlined in red is equal to 9 minus 2x, and this part right there is equal to 24 minus 2x. Hence, these are my answers to AI and AII. Show that the volume B of the box is given by this expression right there. So the volume of the box is equal to its length multiplied by its width multiplied by its height. And we have already obtained the values of the length and the width, or the expressions for the length and the width, 24 minus 2x and 9 minus 2x. The height is this part right there, which is equal to x. When I cut off the corners and fold down the right side and left side, I shall get a height of x represented by this part right there. So try to imagine a piece of cardboard being folded into a box, and hopefully you shall be able to see that the height of the box is equal to these parts, which are all equal to x. Hence, volume equals length times width times height, 24 minus 2x times 9 minus 2x times x. And what I've done is I've taken this x and distributed it onto this bracket to obtain this bracket right there. So I have two brackets multiplied by each other, and I do some simple expansion to obtain this purple expression, and then some simplification of combining like terms to obtain this final expression right there, similar to the one provided in the question. Next, in question C, I'm required to find dB by dx, the derivative expression of B, and there is your answer to this right there. This is simple differentiation. In question D, I'm required to find the value of x, which gives the maximum volume of the box, and then to calculate the maximum volume of the box. So of course we know that the maximum volume is given, or B maximum shall occur when B dash equals 0. B here represents the volume. Or V maximum shall occur when V dash equals 0. The letter doesn't matter. But what we need to conceptualize is that we need to find the derivative function, which we already have, and set it to 0 in order to find the value of x that maximizes the original function. So once I obtain this value of x, I shall simply substitute it into the original function in order to obtain the actual maximum volume of the box. So what I've done here is I've realized that B maximum occurs when dB by dx equals 0 or B dash equals 0. So I've set this red expression to 0, and I've taken out a common factor and attempted to factorize. Of course, you can do this using your GDC equation solver, or you sketch the function and find the x-intercepts. But anyway, the manual approach is also nice. So the two values of x that should satisfy this purple equation are 2 and 9. So which of these values would I choose? Obviously 2, because if I were to choose x equals 9, then the width right there would be 9 minus 18. If I plug 9 into this equation, I would get 9 minus 18, and the width would be negative. And this is, of course, physically impossible. Hence, I should realize that the value of x that I shall choose is this 2 right there. Once I figured out the value of x that maximizes the volume, I can simply find the maximum volume by plugging this x right there into the equation for the maximum volume, which is this equation right there, which I have rewritten in blue right there. So 24 minus 2x becomes 24 minus 2 times 2, which is 4. And 9x minus 2x squared becomes 18 minus 8, and your answer is 200. And this concludes our question. Take a minute to write the answer down if you will, and I shall begin the next question shortly. So the second question that we shall solve came in paper 2, May 2016, time zone 2, question 5. Kindly take a minute and attempt to solve, and the answer shall follow through shortly. So again, you are told that you have a rectangular piece of thin cardboard 16 by 10. The guy decides to design a tray with it, and the tray shall look like this. He removes from each corner the shaded squares of side X, and the remainder is folded up as shown. This is exactly the same as the previous problem, and using the same logic, the remaining length shall be given as follows. This component right there is given by 16 minus 2x. This is the remaining length, which is this part right there. And the remaining width shall be given by 10 minus 2x, and this is represented by this component right there. And the height x is represented by this component right there. So for the purpose of question A, the length is 16 minus 2x and the width is 10 minus 2x. Moving on, in BI you are asked, state whether x can have a value of 5 and give a reason for your answer. Of course, x cannot have a value of 5 because, as we said, this part right there is 10 minus 2x. So if x were to equal 5, this component would be 10 minus 2 times 5, or 10 minus 10, or 0. So if x were to equal 5, I would have 5 centimeters here and another 5 centimeters there, and the middle component would vanish entirely because the sum of these two components is 10, and this covers up the entire width. So the answer to BI is no, you cannot have a value of 5 because the width would be 0. So write down the interval for the possible values of x. X is between 0 and 5. So x is greater than 0 but less than 5. So let's take a look at the answers. There are the first three answers that we have covered so far so that you can keep track. The domain for x is from 0 to 5, but bear in mind that these are strict inequalities, meaning that it is 0 less than x, not 0 less than or equal to x, and x is less than 5, not x is less than or equal to 5. Next, you are required to show that the volume of the tray is given by this expression, and we simply multiply length by width by height. So the volume is equal to length times width times height, 16 minus 2x times 10 minus 2x times x. You should be familiar with this if you've covered the last question in this same video. So I'm going to again distribute the x over the 10 minus 2x, obtaining 10x minus 2x squared, and then I'm going to multiply the two blue brackets right there, getting this expression, and then I'm going to add these two common terms together, getting this final red expression for the volume, which matches the one that was given in the question. Next, in question D, I'm required to find dV by dx, and I simply differentiate this red expression right there, obtaining an expression for V dash in green right there. Then in E, I'm told, using your answer from part D, find the value of x that maximizes the volume of the tray. And as we've mentioned previously, the value of x that maximizes the volume of the tray is the value of x that sets V dash to 0. So V maximum occurs when V dash equals 0. So I just need to solve this equation equal to 0 and find x. After I found x, I plug it into the original equation in order to find the maximum volume of the tray. So this is what I've done here. In order to get x, I've realized that V maximum means that V dash equals 0, and I've solved this green expression equal to 0, and I've obtained the value of x. It's either 2 or 6.67. Obviously, I choose x equals 2 because we've already shown that x cannot be greater than 5. There is my domain of x, the possible values of x. So I have to choose the 2. Next, as we said, in order to find the maximum volume, I simply plug the 2 into the original equation right there. So, or the simplified version right there. You can plug wherever you want. Anyway, either way, you're going to get this expression and this value for the maximum volume. So you just plug 2 into any of the equations in question C that express the volume. Finally, you are told sketch the graph of v equals 4x cubed minus 52x squared plus 160x. So this equation right there, we want to sketch the graph of it for the possible values of x found in part Bii, which we have found to be from 0 to 5, and the range is from 0 to 200. Clearly label the maximum point. So I've written the function down on my GDC, and I've adjusted the x and y values of the window according to the problem statement, and this is what my graph looks like. I'm required to clearly label the maximum point, so let's find that out using the GDC. So second, calculate maximum. You need to provide a left bound and a right bound and a guess. So you are told that the maximum point exists at x equals 2 and y equals 144, and this should confirm that our working is correct because we found the same numbers using the manual approach. There is our 2 and there is our 144, and using the GDC we have found that indeed the maximum point lies at 2 and 144. But of course you might wonder why we did not do this using the calculator to begin with. Why did we have to go through differentiation in E and then substitution in F when we could have just used the calculator function to obtain these values? Well, the reason for that lies in the wording of the question. It says using your answer from part D. So you have to use the derivative and set it to 0 and solve and so on and so forth. So this concludes our question in this video. Take a minute to write the answer down if you will, and maybe also check the marking scheme requirements for the sketch to know what they expect to see in the sketch. Anyway, this wraps this video up. I hope you have found this useful.